So coming to the most interesting thing, where did the stir go? Okay. Oh, thank you. So the luminosity, again, as you can notice by this luminosity is also in a logarithmic scale. So between two gaps, the difference in luminosity is not equal. Like what you generally see on graph. So this is a logarithmic scale. And I think it's quite self-explanatory. Higher luminosity means brighter star, lower luminosity means dimmer star. Now, we have to remember that this is the luminosity of the star, not how the luminosity or the intensity that appears to us. So if I have a very bright star, which is very far away, it will appear dim. If I have a less bright star, but quite close to me, it will appear quite bright. For example, the sun. Sun appears quite bright, in case you didn't know. Sun is bright, it's hot. So, luminosity in more physical terms is called energy output per unit second. So, how much energy the star is outputting in 1 second, which is in joules per second, also measured in watts power. So, combined, this thing is, by the way, with respect to the sun, not absolute value. So, the sun will be somewhere over along this. So it's one solar unit. Alright, the last technical detail of this HR diagram. As we talked earlier, we can relate the temperature to the color of the star, but that's just one axis, okay? So that's just one axis. We need something to define luminosity as well. So Morgan-Keenan luminosity classes came into being. Basically, depending on these classes, we can tell what kind of star it is. Because of the same temperature, I can find two stars that are very different from each other. For example, at a temperature of about 4000 Kelvin, I can find a star over here, or I can find a star over here as well. And these two stars are very different from each other in terms of what they are fusing inside them, what are their properties. So we need another classification that tells us that when I have a particular spectral class, what kind of star do we have here? So we have this Morgan-Keenan class. So the highest, there are supergiants. Luminous, I won't talk about all of these individually. Stellar evolution is another session. Stellar evolution is also another session. Anyway, just so everyone knows, our sun is a main sequence star. Okay, a main sequence star. What does it mean to be on the main sequence? These stars are fusing hydrogen into helium, as we talked before. Since every star fuses, and in its core, important. This thing is important. So it's fusing hydrogen into helium in its core, and that's why it's called main sequence. After is a main sequence star, and since this is one solar luminosity, if I draw it over here, why does this feel slightly off? I'm not sure if this is horizontal, but our sun should be somewhere over here because it's on the main sequence line of the HR diagram. I think I have on the next slide. Yes. Oh, I have to change the HR diagram to something more cartoonish because I couldn't find the HR diagram with sun labeled properly. So our sun is over here, and our sun is called G2b, which is G2 is the spectral classification, which is the Harvard one, and B is the Morgan-Keenan. So we join Harvard and Morgan-Keenan, and then we can label every single star. Question again, is this a star? White dwarfs are white dwarfs stars. Sorry? Yes, okay. So I'll just label yes and no. How many of you say it is a star? So I have one yes at least. Someone supporting me. Yes and no. Yes. Okay. Anyone else? Okay, I'll move ahead. Actually, white dwarfs are not really a star. White dwarfs are cores of stars. So you have different layers of a star. And like the innermost center is what we call the core. So when a low mass star, something like a sun, when it will reach the end of its life, it will not have enough mass to turn into a neutron star or a black hole, which is quite sad. Our sun is below average. And it's fine to be below average. So all the outer layers will just go away. You will be left with the core, and this core is what we call white dwarf. That's why white dwarfs are slightly harder to observe because they are not as luminous as the rest of the star. And I think it's pretty clear, like they are in this scale range. So the very little luminosity over here corresponds to 10 to the power -3, which is quite little, if you ask me, in astronomical perspective. So yes, our sun is a Jupiter star, white dwarfs are a star. This means that even though Hertzsprung-Russell diagram was initially meant to plot stars and make sense of stars, we have just added anything that we want on this diagram. We use this as, we have added so much. So sometimes you'll see other kind of stars, for example, brown dwarfs sometimes plotted on the HR diagram. This is very weird because they are failed stars. Why are we thinking about them? We talked about that earlier. Anyway, we'll move on. Oh yes, a note. Oh, be a fine girl, guy, gender, kiss me, those classifications old. We have come up with more spectral classes now. Class LTSC. I was reading a book and the new mnemonic to learn it is, oh, be a fine girl, kiss me, let's talk. We are all about the way, but whatever. There is no standard version of the HR diagram. What this means is that if you look at different sources, you'll get a slightly different plot. Maybe on the luminosity axis, instead of having it in terms of solar luminosity, you'll have it just absolute magnitude, not the luminosity. So you can edit this diagram according to your needs. And this deserves a much more rigorous treatment, in which neither I have time nor expertise. This is grammatically correct. There are so many things. For example, what we talked about earlier, the variability of the stars, the radius of the star, volume of the star, everything can be plotted on the HR diagram. But I thought maybe we'll just talk about the axis because they're quite important. So, has the HR diagram ever been used for something important? Yes. This is one of my favorite uses of HR diagram. Something called blue stragglers. I just find them extremely fascinating because of their names. Like they are left behind, blue stragglers. Story time, I guess. In this paper, which was done by this guy called, I forgot the name of the scientist, I apologize. Alan Sandage, if I remember correctly. Please fact check me. Alan Sandage. I know I made these slides and I forgot the name of the scientist. If I remember correctly, this was this one. So he was plotting the HR diagram for, he called it the color magnitude diagram, as I said. So he plotted the B minus V values and the magnitude of the star. Of this cluster, a globular cluster called M3. This is another HR diagram of a globular cluster called M55, but this was the original paper that I took the screenshot from. So ideally, let me erase this. How the HR diagram of a globular cluster should look like is you have this main sequence and then it just goes somewhere over there, rough, and then you have something. So you have this turning point in all the diagrams of globular cluster. Won't go into too much detail, this is called the turn-off point, but this is not the main idea. When he plotted the diagram, he realized that there are these stars that are still following in the main sequence line, but they are after this turning off point. which was not observed ever. So he called them the blue stragglers because they are closer to the blue side of the HI diagram and they are left behind. So they are blue stragglers. Till this date, we do not have a general consensus. Why do blue stragglers exist? There are multiple theories, obviously. Maybe other stars transfer their mass. These stars, which cause them to increase the mass and make them blue, blah, blah. But we don't really know why blue stragglers exist. And we don't really know much in astronomy anyway. They are quite sad field of science. Anyway, yes, that was all. Apart from the crazy animation that we did, yes, if you have any questions, you can ask now, later, whenever you want. And the last line is just for myself. I don't know why I wrote that. Anyway, as everything goes, we'll game time. The thing is, every single week we've been doing the star chart thing, and I thought maybe we should spice things up. So we are still doing this star chart, but it's individual and actual prizes for top 3 winners. Like you can actually eat them. And I apologize for the last week. There was a slight miscommunication. I hope everyone got their one piece of chip. Oh yeah, because we were supposed to have a prize for everyone, but it was miscommunicated. A prize for one person, so there was one packet, one chip. So everyone got one chip. So today's game is something. The reason, I'll just explain the reasoning is actually a real reason why.